Welcome back, everybody. We are getting set up for Jonathan Birch's presentation on the dangers of serialization and deserialization. While he is doing that, we actually have a set of handouts that he prepared that should be circulating through. If you do not have them, right up here towards the entryway is a lovely person who will help you get a copy. .NET is a pretty magical beast. It will run damn near any code you feed it, which is fantastic in terms of the versatility and the utility of the application set. The problem is that you need to be careful about what you are feeding it, or you will get undesirable and often insecure outcomes. Jonathan has been instrumental in helping beat the drum inside Microsoft and outside Microsoft on how to do this properly to ensure that you enjoy all of the benefits of this broadly deployed, very flexible platform without trapping yourself into an insecure deployment from which you have a hard recovery path. So without further ado, to give him the full amount of our time, quick round of applause for Jonathan Birch.
Thanks. So like you said, I'm Jonathan Birch with Microsoft Office Security, and this is Dangerous Contents Securing .NET Deserialization. In this talk, I'll cover how insecure use of serialization in .NET can lead to remote code execution vulnerabilities, and then I'll tell you how you can prevent those sorts of vulnerabilities. I'll give advice for specific serialization APIs, and I'll tell you how you can scan for serialization vulnerabilities in your products. So first, some background on serialization itself. What is serialization? Well, it's a process where you can take in-memory objects and convert them into something like a stream or a string so that you can store them or transmit them. It's usually used so that you can restore those objects either somewhere else or at a later point in time. Serialization is usually used to transfer data, often between clients and servers. It's also used to back up data to a database so you can restore program state. And it lets you create equivalents between objects in different environments, so JavaScript objects versus .NET objects, for instance. So then how can serialization be exploited? Well, first, there's lots of serialization APIs out there. And many of them will do this thing where when they're deserializing a stream, they'll determine what types they're going to make by information from the stream itself. So they're actually storing the type information in the stream. And second, it's often the case when serialization is used that it's being used in such a way that the stream that you're going to deserialize was at least temporarily in the hands of an untrusted party, say a client user. In combination, this means that there's an opportunity for an attacker to inject other types into that stream that your process is going to deserialize. And then you're going to create instances of types you didn't expect. So why is that a problem? Why is it going to be bad if you make instances of types you didn't expect? Well, first, it's not going to be the case that an attacker can attack a deserialization process just by creating their own malicious class and getting you to deserialize it. Deserialization is only going to work if the deserializing process has knowledge of the type definition that it's going to need to make. Instead, what you're going to do is an attacker is going to leverage either types in your program or types defined by the framework. .NET has a lot of types in it, and a lot of them have code that will run just because you created an instance of them. Now, different serialization APIs work differently, but many of them will call constructors on classes that they make instances of, or on deserialized handlers, or sometimes setters for properties they set. And it doesn't matter what API you're using. If you're creating an instance of a type and it has a destructor, if that object gets garbage collected, that destructor is going to be called. Now, these methods can have side effects, and it turns out that you can combine the side effects of multiple types to create gadgets that allow for things like arbitrary code execution. Here's sort of a simple example. So binary formatter plus temp file collection. Binary formatter is probably the most commonly used serialization API in .NET. And if you're using binary formatter to, say, deserialize a stream that you don't trust, and an attacker has access to that stream, then one way they can attack it is using the temp file collection type. Temp file collection is a type in .NET which is used to manage sort of a list of temporary files. And what it will do is when it's garbage collected, it will try to clean up those files and delete them. So what an attacker can do is if they have a stream that you're going to deserialize, they can create their own temp file collection object, add a list of files to it, serialize it into the stream, and when your process deserializes it, you'll get an object that when it gets garbage collected will delete some files in your context. Here's a diagram of that scenario. So here you've got a client-server application where you have like a purchase order that's being serialized by the client, sent to a server where it's deserialized and processed. An attacker takes this system and instead serializes a temp file collection object and sends it to your server. And this is sort of like a bomb. It's going to go off when it gets deserialized. So the server deserializes this object, and then it deletes a bunch of files potentially, maybe the web.config. That's a good way to take down a server. And this is not the best attack. It's just a simple one to explain for binary formatter. I encourage you to read James Forshaw's Exploiting.NET Managed DCOM presentation. He outlines a way to get arbitrary remote code execution through binary formatter. It's just a little more complex than I can explain in a 25-minute talk. So why is this a problem? Well, remote code execution is not something any of us want, but it's also a really common issue. So this vulnerability used to be present in a large number of Microsoft products. We fixed every issue that we've known about. If you found one, please let us know. It's still the case, however, that you can easily find web applications out on the internet that are vulnerable to this type of attack. That's not something we like, but we can't really go and approach everyone we find on the internet who has potentially vulnerable applications. So why don't we fix this instead by just making it so .NET doesn't have dangerous types? Why don't we just take all the types that have potential side effects for constructors or setters or destructors and make them so that they're safe for deserialization? Well, it turns out that's not really practical. .NET has hundreds of thousands of types, and frequently these side effects that are dangerous are going to be dangerous because of the functionality provided by the type itself. We couldn't change that functionality without, at the very least, breaking framework compatibility. And really, if you've got an application framework and you can make arbitrary in-memory objects, that's probably a win condition for any attacker. It's not going to be the case that you have some other library that you could be running on that you could do this and it probably would be OK. So really, the only solution to this problem is for .NET application developers to only use serialization securely. And you might be saying, OK, that's binary formatter, but I don't use that. Well, first, you might be. It turns out there's a lot of .NET APIs that use binary formatter behind the scenes. So anything that reads resource files does it. If you use ASP.NET with view state, sort of the classic mode, that uses binary formatter. And I'll go back to that a bit. There's various other formatter APIs in .NET. Object State Formatter, LOS Formatter. Other APIs like Net Data Contract Serializer will do this. There's a longer list in the handout and at the end of this slide deck. And really, even serializers that don't use binary formatter can be vulnerable. So JavaScript serializer. You would expect JavaScript serializer to be safe. And by default, it actually is. By default, JavaScript serializer won't take type information from a stream it's deserializing. So you're not going to be able to make these sort of jack-in-the-box objects that will do bad things when they're deserialized. But you can use JavaScript serializer with a JavaScript type resolver. And if you do what people usually do and set a symbol type resolver, that just makes any type it's asked to. This makes it similar to the binary formatter scenario again. However, JavaScript serializer is a little bit different. It will only instance types that have a public parameterless constructor, and it will only set values for properties, not private members like binary formatter will. On the other hand, it doesn't care if a type is serializable. So it is exploitable, but the sorts of exploits you get are different. And I want to credit Alvaro Munoz and Alexander Mirosh for publicly talking previously about JavaScript serializer exploits like this. So here's a simple payload for JavaScript serializer. This is a JSON string, which is just going to make an instance of an XML document object and set its inner XML property. So XML document has a setter on its inner XML property, which will just parse the XML that you give it immediately. And XML document also will process document type definitions. So this gives you essentially an XXC, file exfiltration or server-side request forgery. And you'll note for JavaScript serializer, the deserialize call actually has a type that you pass to it that doesn't do anything if you're using a type resolver at least. It's only there for the case where there's no type resolver to determine what the root object type will be. So that's a couple of internal or like .NET defined serialization APIs, but there's lots of third-party serialization APIs that exist also, and many of those are also exploitable. So there's JSON.NET, made by Newtonsoft. JSON.NET, similar to JavaScript serializer by default, doesn't deserialize type information from the stream. But it has a type name handling property, and if you set it to any value other than its default value of none, you're back to the same situation where it will take type information from the stream. So here's a simple gadget to get RCE from JSON.NET. It was developed by Levi Broderick at Microsoft. And what this is, it's a JSON string that when deserialized by JSON.NET, if type name handling is, say, auto, will create an instance of a Windows identity object and then set its claims identity.bootstrap context property. It turns out Windows identity has an on-deserialize handler that will just try to use binary formatter to deserialize that bootstrap context property when it itself is deserialized. And this just lets you wrap a binary formatter exploit inside of a JSON exploit. Then there's service-stack.text. This is an API I looked at myself because people in Microsoft are wanting to use it. It's a little bit different. It's a templated serializer. So when you do a serialization or a deserialization, you have to give it a type. And although it puts type information in the stream, it tries to make sure that the types it deserializes match up with the ones it's expecting based off of the type you gave it. However, it allows for polymorphism. So what will happen here is you've got a root type, and the stream says, well, this is what the type I want you to make for that root object. And it will say, well, is the one type assignable from the other? If so, it's OK. Otherwise, throw an exception. And then we'll do that for each member and all of their members and so on. And it turns out that if you can walk to an object type, a member of type object, well, that's a wildcard. That'll let you create any type you want. So that's going to be the point where you have an exploit. And in .NET, because there's a lot of innocuous-seeming types that have a very large number of subclasses, it's actually almost always the case that you can walk somehow through a membership graph to get to a member of type object. I give an example here for a way to do it with system.exception. You can do it with lots of other things, too. So once you walk to a member of type object, this would let you do an exploit. This is the same as a JavaScript serializer, where it's an XML document where you're setting inner XML. Their formatting is a little bit different for what they want. I did contact the maintainers of service-stack.text about this vulnerability through Microsoft Vulnerability Research. And they did update their API to try to prevent this. What they did was they added an additional whitelist, which says, or an allow list, rather, which says that the only types that they'll create are the ones that you add to the list or the ones that they put there by default. The ones they put there by default, however, is every class that implements iSerializable in .NET, which is a ridiculous number of classes. I don't know a way to exploit this. I don't know if there isn't one. So I've outlined how different serialization APIs could be exploited. Now I'll tell you how you can prevent those exploits. So in general, deserialization vulnerabilities are only going to be present with 3 ingredients. You have to have a stream you're going to deserialize that some attacker could have modified. You're going to have to be taking type information from the stream so that someone can stick a type in there you didn't expect, and it can go off like a bomb like this. And you're going to have to be not constraining the sort of types that it can create during deserialization. If you remove any of these, you're going to prevent deserialization attacks, although admittedly the third one here can be a little bit tricky. So for the first of those, protecting the stream, this is really the easiest way to prevent deserialization attacks. If you only deserialize streams that you serialize in the first place, you're generally OK. If you keep your stream on the back end, that's probably all right as long as you don't have some other way for a user to modify it with like a SQL injection attack. Alternatively, if you're going to give the user the stream to hold on to for a while, like in some cases you see this where a server will give the client the session state object and it's serialized. You can give them an HMAC to go with it. If you validate that HMAC before doing your deserialization, the user shouldn't be able to change the stream and also have the HMAC still be valid, so they can't really inject their own objects. The HMAC can also be useful for the case that you're storing a serialized stream in a database as long as you keep the secret for the HMAC somewhere other than the database. Another thing you can do is just use a serialization API that doesn't take types from the stream. So data contract serializer and XML serializer are both safe as far as this goes. And JavaScript serializer and JSON.NET are OK as long as you don't either set type name handling or add a JavaScript type resolver. They're safe by default. That said, you can make all of these exploitable by adding some other mechanism for an attacker to determine what type will be used for the templating of the deserialization. There have been cases where, for instance, data contract serializer was used. However, they added next to the data contract serializer stream some other element that said, and this is the type you use for your template when you do deserialization. As soon as you do that, it's exploitable again. The third way you can do this, and the tricky one, is to constrain the sorts of types that are allowed during deserialization. I don't really recommend this. It's very difficult to do right, but it seems sometimes it's necessary for certain application designs. So what you're going to do is you're going to essentially create an allow list for the types that can be created during deserialization. It's hard to do that correctly because there's lots of types in .NET that seem innocuous but are actually dangerous to deserialize. Hash table is an example of this. You would think hash table would be safe to deserialize, but it actually has a member which says this is how much memory you should allocate for the hash table. And certain serialization APIs will let you set that member and will then cause the hash table to try to allocate potentially arbitrary amounts of memory, which lets you at least get a denial of service attack off. So the way you want to do an allow list is not this. If you do a typecast after an insecure deserialization, that's not going to actually provide you with any security. Most gadgets that you can get code execution through for deserialization will have already executed before you get an invalid cast exception for this sort of thing. Instead, the sort of OK way to enforce an allow list for your deserialization is to use a serialization binder. You can do that for binary formatter. You can do that for JSON.NET. There's a few other serialization APIs that also allow you to specify a serialization binder. And the way you're going to do that is you're going to subclass a serialization binder type. You're going to override the bind the type method. And you're going to throw an exception if that bind the type method gets called with a type you didn't expect. You need to keep in mind that your binder is going to be called for every type involved in the deserialization, not just that root object that you're trying to deserialize. So if your object has members and those objects have members and so on, each of those types is also going to be called or passed through to your bind the type method. You also want to make sure that you're doing one-to-one type matching with this. So you don't want to use is assignable from. You don't want to allow polymorphism. That gives you the same sort of vulnerability I was explaining with service.text. You also can't just return null when you see an unexpected type. You have to throw an exception because when you return null, certain serialization APIs will just fall back to a default binder. And when that happens, the default binder will just create whatever type it's asked for, and you don't achieve anything. And you don't want to use reflection. So first, if you're trying to use reflection to compare type against type instead of type name against type name, it's going to be really slow. And you're also creating a situation where an attacker can maybe make your process load assemblies you didn't intend to. So here's an example of a good serialization binder. Here we're subclassing the serialization binder type. We're overriding bind to type. We have this list of tuples that map string to type. And whenever we're called with a type, we make sure that it matches one of the type strings. If it does, we return that type. If it doesn't match any of them, we throw an exception. That's the way you want to do it. And now I'll give you some advice on specific serialization APIs. So for binary formatter, don't use binary formatter to deserialize an untrusted stream without a binder. That is the classic deserialization vulnerability. It's the one you can find everywhere. Just avoid doing it. If you're using binary formatter, you might consider using some other serialization API instead. Data contract serializer and XML serializer often do the job that people are trying to do with binary formatter. Alternatively, if you're using binary formatter to deserialize a stream that you want the user to hold on to, again, an HMAC is a good idea. ASP.NET ViewState. So ASP.NET ViewState is actually serialized and deserialized using binary formatter. This means that if an attacker could actually modify the view state, they could get RCE on your server, which is pretty bad. So ASP.NET by default has an HMAC that it associates with that view state to prevent it from being modified. The trick with this is that the secret used for the HMAC on view state is just a machine key. This means that if anyone can get access to your machine key, then you can reproduce the HMAC, make their own view state, stick it in a query string, and get RCE on your server with a GET request. So you need to treat the machine key for a classic ASP.NET server as equivalent to an admin password. It needs to be difficult to guess and completely protected however you would protect passwords. JSON.NET. Don't use JSON.NET to deserialize an untrusted stream if you want to set with type name handling set to anything other than none. If you have to have type name handlings for polymorphism or something like that, use a serialization binder. Serialization binders for JSON.NET are exactly the same as the ones for binary formatter. JavaScript serializer. Don't use it with a JavaScript type resolver. If you're going to actually use JavaScript serializer to deserialize an untrusted stream, don't allow for any method where an attacker can choose the templated type either. Service.text. My recommendation for service.text is to only use it to deserialize streams that you absolutely trust. If you want to use it to deserialize an untrusted stream, you have to make sure that the membership graph for the object that you use in your template can't possibly contain a member of type object. That's ridiculously difficult to do. So how can you scan for serialization vulnerabilities then? Well, first there's an obvious thing. You can look for potentially dangerous serialization APIs in your source code. You can do this just by grep or text-based search. There's the APIs themselves, and there's also indicators that APIs are being used insecurely. So if you see type name handling at all in your source, it probably indicates that someone is using JSON.NET in an unsafe way. Similarly, if you see simple type resolver, it's an indicator that JavaScript serializer or a related serializer is being used unsafely. There's a couple of tricks you can use for dynamic analysis for this too. So there's a common anti-pattern where binary formatter is used with a base64 encoder, and then the string that's produced is put in, say, a cookie, a query string, form post data, things like this, sometimes even in like file contents. And when you base64 encode a binary formatter serialized stream, the resulting string always begins with the all-caps string AAE, AAAD. What you can do is you can look in your web traffic logs for that string. If you see it, it's a strong indicator that you have a potential serialization vulnerability. Similarly, $type and __ type can indicate cases where some other serialization API is being used in such a way that the type information is taken from the stream. That's going to be JavaScript serializer, JSON.NET, service stack.txt. So that's another thing you can look for in web traffic logs or sometimes even in file data. And that's my presentation, if there's any questions.
That can't possibly have explained everything everybody has ever wondered about serialization and deserialization. There we go. We have a question in the back.
Hi. On your sample serialization binder, should you not be verifying the fully qualified name, including the assembly name, as part of that?
Yes, I should.
That was probably the most succinct answer to a technical question I've heard in the entirety of BlueHat, so bravo. Any additional questions for Mr. Birch? What are we going to do when we get home tonight? We're going to check our serialization code, please. We could write a purposefully vulnerable app and have fun with it. Please don't do that. Please don't do that. So this is a set of problems that is complicated because the traditional world of identify the problem, patch the problem, doesn't really apply in the same sense here. Each individual person that is developing in this space needs to take accountability for what their code is doing. There are tools and techniques, and Jonathan's been great about showing you the ways you can start to identify these behaviors and things you might already have deployed. But at a minimum, on a go-forward basis, you need to be thinking about how to use serialization safely to ensure that you don't find yourself in a really messy situation further down the road. So without any additional questions, we have a few minutes as we reset for our next presentation. A big thank you to Jonathan for his time.